So a prime number is a number that is divisible only by 1 and itself, and all the other numbers are called composites. And that will basically be all for today. Well, mate, how do I stop the recording? There are two theorems involving primes that I would like to really take care of with you today, guys. So first of all, whenever we have a prime p that will divide a product of some n numbers, it will mean that that prime divides at least one of the numbers that take part in that product. And second of all, we will have the fundamental theorem of arithmetic, which basically states that every single number, whether it's composite or prime, well, it is then expressible as a unique product of prime numbers. Honestly, I have no idea what I can say more. What do you think, mate? No. Okay, so I think I'm just gonna, let you watch me proving all those statements, and then maybe, solve some problems on the board. Here I am. Okay, guys, so, we are working our way up, towards the fundamental theorem of arithmetic, but first of all, we need to prove one, big and huge lemma, which is the Euclid's lemma. So we are supposed to prove that, whenever we have a prime, let's say p, because, p is a nice acronym, abbreviation for a prime number, yes, so, whenever we have a prime number p, that will divide a product of some, let's say, n numbers, then it will imply that p will divide at least one of those numbers. So let's say that, p will divide, let's say, ai, with I that will be between 1 and we are supposed to prove that statement right there. Lovely. So I would like to conduct this proof using induction. I would like to induct on the number of variables involved in the product that p is actually dividing right there, so on n. Lovely. So first of all, let's try and do the base case. The base case, I would like to I would like to check for the case or I would like to set the base case to be the case of n equal to 2, because n equal to 1 just doesn't really make any sense, because if p divides a number, it divides this number. It's all, lovely. So for the base case of n equal to 2, or maybe I will write it not here but here. So for the case of n equal to 2, we would like to prove that whenever p divides, let's say, a times b, so I don't have to write those subscripts like a1 and a2 because it's annoying, then p divides a or p divides b. Lovely. So, first of all, I would like to suppose two things. Suppose. First of all, that p divides a times b, and second of all, I would like to suppose that p does not divide, let's say, a. So, given those two, we would like to prove that p has to divide b, or, it doesn't really make any sense. Any other way around. Lovely. So, p does not divide a. What does it mean for us? If p does not divide a, and, p is a prime number, then, the greatest common divisor of p and a is a 1, because, the only numbers that actually divide p are 1 and p itself. And so p and a are co-prime numbers. Actually, whenever we have a prime that doesn't divide some particular composite number, then that prime and that composite are co-prime to each other. So, we are actually getting that the greatest common divisor of p and a will be equal to 1, as you probably remember from the episode about GCD and LCM, of this beautiful theorem right there, that whenever two integers are co-prime to each other, there are two more integers, so let's call them maybe x and y, such that x times one of those integers that are co-prime to each other, plus y times the other integer will be equal to a 1. And well, that's absolutely perfect because, well, by our first it's an assumption, it's a supposition, it's not whatever. From our first condition right there, we get that a times b will be equal to some natural number, maybe not n, because well, n is already taken, let's say k times our prime number p, yeah? Lovely. And so, well, that's actually pretty neat, because if we were to, let's say, multiply both sides of this equality right there by a b, what we would get is, well, this messy x times p times some b, well, basically number theory is just messy when it comes to multiplying weird stuff together, times y times a times b. This b is too high. Yeah, y times a times b is equal to b, but what is a times b? Well, a times b is some integer, k times p. And so what we're getting is x times p times b plus, well, y times k times p is equal to b. And so we can do what right now? We're gonna go on and factor p out of this equality, getting p multiplied by x times b plus y times k is all equal to b. And so, well, ladies and gentlemen, this is exactly what divisibility is. We get that p multiplied by something is equal to b, and so, well, p has to divide b. Yeah, that's absolutely perfect, because, well, this is exactly what we're supposed to prove in this base case right there. Perfect, yeah. So now we can move on and we'll prove the real theorem right now using induction. So I would like to suppose that, maybe I would like to assume that for, let's say, n, we have that p divides a1 and a product with multiplying stuff up to an. And it will imply that p will divide some ai with I between 1 and n. Yeah, perfectly. And so right now I would like to, we'll do the inductive step. Yeah, I'm writing, I'm naming those parts of the solution longer than I'm actually solving the problem. Yeah, so the inductive step would be that, well, p is set to divide a1, a2, where multiplying stuff up to an times an plus 1. Yeah. Okay, so, well, I would like now to kind of, well, treat those n plus 1 numbers as two separate composite numbers. So first of all, this guy right there, the product from a1 up to an, I would like to call this maybe a, let's say. And a sub n plus 1 I would like to call, let's say, b. Yeah, that's perfect, because, well, now what I'm getting is p dividing a times b, but, well, from our base case we get that, well, if p doesn't divide one of them, it has to divide the other. And so, well, right now it doesn't really matter which one you choose to which one we choose such that p doesn't divide it. We get that p will divide a or will divide b. So, well, substituting in this those products for a and b, we're getting that p divides either a1 up to an, or p divides a sub n plus 1. But what we're really getting here is, well, by the assumption we made earlier, this means that p will divide some number, some a sub I, with I between 1 and n. And so, well, combining those two together, we actually get that p will divide some ai with I between 1 and n plus 1, which is exactly what we were supposed to prove in the inductive step. And so, ladies and gentlemen, the Euclid's lemma is most certainly proved. Oh no, proven. Whatever, English stuff. Okay guys, so the fundamental theorem of arithmetic tells us that every single integer out there is expressible as a unique product of some prime numbers. And, well, I would like to divide the proof of the theorem into two parts. So in the first part I would like to prove that every single number is expressible as a product of some primes. And in the second part I would like to prove that every single one of those products is a unique representation of that number Just absolutely perfect. So first of all, I would like to prove, well, I know we can prove that, but whatever, prime factorization, yeah, prime factorization, perfect, yeah. So every single number out there is expressible as a product of primes. Okay, so well, we have basically two cases right there. So the first case would be that, well, let's say our number that we're dealing with, so n, is a prime number, so it's equal to p. Well, then it's kind of done. It works. It just does. Yeah. And so for the second case, we're getting that n is composite. N is composite. Lovely. Well, if n is composite, it is not prime, and so it is divisible by some numbers other than itself. And so it is, it is divisible by at least two numbers. And so, well, those numbers are definitely less than n. So I would like to do this one by induction right there, the induction on n. So for the base case, let's maybe take, some numbers that are just, close to zero. Some natural numbers close to zero. I'm only proving this statement for the positive numbers because, well, for negatives it works just the same. The proof goes just the same, but you just have to write that negative sign everywhere all the time. And I'm too lazy for that. You can try this as an exercise for the watcher, not for the reader this time. Yeah. So for the base case, I would like to maybe say that n is equal to, well, one doesn't really work because it's neither composite nor because it's not either composite or prime. 2 is prime, 3 is prime, 4 is not prime, so n equal to 4. Well, n is 4 is equal to 2 times 2, so well, I guess that's enough for the base case right over there. Yeah, lovely. And so right now I would like to assume that all numbers up to n satisfy the hypothesis. Yeah, lovely. And why am I doing that? Because, well, as I've already said, if n is a composite number, it has at least two divisors, yeah, that are not itself and that are not a 1. And so we can say that there exists two numbers that are greater than 1, let's say a and b, that are also less than n, such that a times b is equal to n. But, well, by our assumption right there, we get that a will be equal to, well, some primes, p1 up to, let's say, pl, yeah, because why not? And b will be also a product of some primes, let's say q1 up to qm, because why not, yeah? So, well, what it means is that actually n will also be a product of primes, because it will be a times b, which is equal to, well, those p1 up to pl multiplied by q1 up to qm, which actually, well, proves our statement and, well, proves that every single number, no matter if it's prime or composite, is expressible as a product of some number of prime numbers. And I think we can tackle the uniqueness right now. Okay guys, perfectly, so now we can tackle the uniqueness of those factorizations. So we're supposed to prove that factorization gives a unique representation of every single composite numbers in terms of some prime numbers, and more specifically the products. Just absolutely perfect right now. So I would like to do this one by induction. I would like to first of all just, well, make an assumption, assume a statement for, well, let's say some case that are strictly greater than 1, because, well, it doesn't really make sense for 1. I mean, this statement doesn't really make sense for 1. It doesn't have a representation in terms of a product of prime numbers. That is also strictly less than some kind of an n. Yeah, well, base case is workable. Let's just take, for example, 4. It has only, well, 2 representations, 2 times 2 and 2 times 2. Those are permutation of each other. Well, perfect, yeah. So, well, now I would like to take myself a number, so let's say inductive step. Awesome. So that I would like to take myself a number n, and I would like to say that n has two representations. First of all, it will have a representation of p1 multiplied up to, let's say, pm, because I like the letter m. Yes, so pm. And it also has another representation of q1 up to qr. Perfect. So now, well, yeah. Well, first of all, it's interesting. There's a nice, interesting thing that, well, if those numbers, right? I mean, if those products are equal, I will now focus on this on this product on the left-hand side. Yeah, I would like to take myself that some, let's say one of those primes. I will take pm just for simplicity. Then it will have to divide the entire product q1 up to qr. I mean, those products are equal to each other, and pm divides this product because it's a part of it, and so it will have to divide this product as well. But well, if p sub m divides the product of q1 up to qr, those look like a's, not q's, whatever, qr, well, this means that there has to exist some q, let's say qj, yes, so pm, such pm will divide that qj for some, well, for some j. And well, they're actually pretty neat because, well, if those are, well, both prime numbers, and prime numbers can't really have any divisors apart from itself and 1, but prime numbers cannot be 1s too, it will mean that pm will actually be equal to qj. Well, that's absolutely perfect because, well, I would like right now to assume without a loss of generality, yeah, assume WLOG that j is equal to r, yes, so qr is qj, because it will simplify my notation quite a bit in the future, yeah? Okay, so well, this means that I can right now create myself another number, kind of like a brother of the number n, let's call it n prime, for example. And n prime will be n, however, without that p sub m and q sub r in its two representations. So it will be equal to p1, and we multiply step up to p sub m minus 1. It's going to be also equal to q1, we multiply step up to qr minus 1. And well, this is going to be actually strictly less than n, because, well, we're divided by something that is for sure not a 1. Perfect. Well, that's really perfect because now n prime, we can use our inductive assumption on n prime right there. Yes, so well, this means that those two are, well, unique representations, so they are permutations of each other. Well, this means by our assumption, that, well, p1 up to pm minus 1 and not p but q1 up to qr minus 1 are permutations, let's say perms of each other. That's perfect. So they are permutations of each other, but let's not just combine it with the fact that p sub m is equal to q sub j, and, well, let's return those two to their respective representations of n. And then by combining this table of facts, and I'm stuttering today, what we're really getting is p1 up to pm, not m minus 1, but m, yeah, and q1 up to qr are permutations of each other. Yeah. And so, well, ladies and gentlemen, this is exactly what we were supposed to prove in this problem. And so, well, after, well, a really difficult fight, after slaying the dragon right there, we finally arrived at the destination where we really wanted to be at in the very beginning of this video. And so we proved the fundamental theorem of arithmetic, and well, I guess I'm going to sleep. I have to stop stuttering. Oh. Okay guys, so let's move on to the problem section. So we're supposed to prove that there are infinitely many prime numbers out there in the wild, in the bush, in the city jungle. So, well, how are we supposed to do this one? And I really love the Euclid's proof of that, because it just, well, so foolproof, yes. So, first of all, I would like to assume towards a contradiction that there is actually a finite number of those prime numbers. So I would like to assume there are n primes out there, yeah? And so let's say I'm gonna have, you know, some p1 as the first prime, p2, and we are, you know, just taking primes up to some nth prime out there, yeah? And so right now, I would like to do is construct myself a number, yeah? So I'd like to construct a number, let's say capital N, that will be equal to the product of all of the primes that we know plus 1. And well, by the fundamental theorem of arithmetic and also by the Euclid's lemma we proved earlier, we have that this number n, yeah, is divisible. I mean, there will be a prime that divides it, yeah, because it is representable as a product of primes. So there's at least one prime that will divide n. Perfect. But well, let's just call that prime pk, and we know that p times pk divides capital N. But well, this means that pk divides p1 up to pn plus 1, and so well, if pk was on the list we made earlier of all the primes, of all the non-primes, well, it would be kind of crappy right there, because it would mean that, well, as pk divides this product right here, it would mean that pk would have to also divide 1, which is a contradiction as hell, like real, big time. And so it means that, well, pk has to be a new prime number, unless it's 1, but 1 is not a prime number, so it wouldn't really make any sense. So we get that pk is a new prime. And well, if you think that it will stop right there and that pk is the last, and p sub k is the last prime out there, well then just create another product of all of the primes from p1 up to pk, add 1, and well, you will get another prime, then another, then another, then another. You can just go on like that indefinitely until you will die, because we're all gonna die. Why even bother? Okay guys, so I really hope you enjoyed this one. I really hope you got some value from it, and I really hope you learned something. If you did, I'm happy you're happy. Maybe you could, I don't know, give me like a thumbs up or some subscribe or whatever. I'll be really grateful for that, and we'll, see you in the next one.